Okay, it's a very interesting talk. Okay, so we are open for questions, please.
Okay, I have a question.
Please, Riddhi, yes.
So when you showed the spectrum of the energy, not energy of the
Action.
right action. What about the energy spectrum? You did not show that. Does that have any?
In my simulation, you mean?
Yeah, the paper that was accepted. Just I was looking at it also.
Let me come back. So I just show here. I just show here the wave action with the compensated by the solution. Well, I mean, this part of the spectrum here is clearly due to a direct cascade of energy. So if I plot the same thing for energy, I will get two regions, I would say, with, well, I mean, two different power laws. The thing is that this region, I mean, for the direct cascade is very narrow. So it is not, I mean, really, I mean, convincing to compare with any power law. Even that for the left part, well, it starts to be convincing because we have, in a region, I would say not a decade, but well, it's close to be flat. But the point of the paper is not to say, okay, we have the power law, is to say we have a dual cascade, we have turbulence, and we have properties that are the one expected for wave turbulence, which is already a big point. Now, for the comparison, we need to increase the resolution, and that's a big problem. For example, for 1000 squared, so 1024 squared, it takes 6 months for the moment. So what I need is to improve the code, and actually I plan. Well, I have, I mean, ideas about that. So that's the next things to do for sure, because I need to increase the resolution to do other statistical analysis.
I have another one. So here you're forcing a pretty high wave number, and I understand that is to show that there is a dual cascade. But do you think that is physically is the forcing, would that happen at a low wave number or high wave number?
Yeah, but what does it mean, low on wave? It must be compared with some wave number, physical wave number, and that's difficult to say, because actually, if I already talked with one cosmologist about that, or I read papers, there is when, for example, for the phase transition, for the gut phase transition, gravitational waves are expected. And then I asked the question, okay, right, can you tell me a frequency? And they said, well, we don't know. We have a range of frequency, and this is actually very big. So the idea, I mean, the numbers are not very well defined. So here, it's difficult to say. I can just say that it must be greater than the Planck scale. I mean, this scale, to apply. I mean, I would say classical general relativity. I mean, not quantum gravity, and. But precisely, it's difficult to say.
Thank you.
Okay, so let me, I had to take time to grasp it. But the elastic wave turbulence similarity, this elastic plate is like a space, right? I mean, so maybe these oscillations of real space, XY, is connected with some plate vibrations. Is that reasonable intuition, or is it rubbish?
From the theoretical point of view, if you develop the theory, you see that it's 4 waves, and also you see that the symmetry is such that we have the wave action conserved, and we have so an inverse cascade, and so the idea would be so weak, and then it becomes strong. So that's the idea, is to say, okay, a lot of things are similar, so why not? Of course, I mean, this is the problem is it's just elastic waves. From a theoretical point of view, there are interesting things. For example, do we have a condensate? What does it mean in this case?
I see.
That's a big question. Well, I don't know if it is possible to do that, because of course we need. I showed you this movie at the beginning where it was a metallic plate, but the situation was also limited. So, well, But I recommend to read this paper by Arseni et al. There are several papers, and the last one, I think this one is very interesting because it's a long paper describing all these properties, and well, I think it is.
I see. So the elastic wave turbulence shows inverse cascade and condensate, or no? I mean, it's not.
No condensate for the moment. I mean, the theory is done for wave turbulence, and they predict and they observe with simulations this inverse cascade. Then the question for strong wave turbulence, I think it is. I mean, people who worked on that, they were more interested by weak turbulence, but the next step, of course, it's strong wave turbulence. So for the future, this is what I mean. I mean, just follow what they do, just to better understand what we do. And
okay, I have one question. So it's I mean, really a very general question. Let's say we have a system where at the weak turbulence level, we don't have any I mean contribution from the 3-wave level. I mean 3-wave like interaction, and the first non-zero contribution or maybe the significant one comes from the 4-level ones. Now let's say in this system the turbulence has switched to the strong regime. Now does it say that always it would maintain in its linear fluctuation regime the 4-wave conservations and always, or it will somehow develop then some triad? I mean, because I mean the only concern is that because the 4-wave thing you did not prove from the first principles, unlike what we do for 3 waves from the Navier-Stokes. So that's my question. If the question is stupid,
no. There are 2 examples. One is elastic waves. You get it directly, these 4 waves, but there are problems where you expect to have 3 waves, and for some reasons, symmetry and so on, there is no contribution. So you go to the next order. Especially, I mean, if you take problems in lower dimension, like in 1D, it's very specific 1D. And I know a problem where you expect 3 waves, there is no. You expect 4 waves, there is no. And you have to go to the 6 waves because it's 1D. So that means for weak turbulence. So that means you can just cancel different orders for different reasons. But there are examples where you get directly, because the nonlinear terms are cubic, you get, for weak turbulence, you get 4 waves, not 3 waves. Now, when we go to strong turbulence, then for the problems where 3 waves, 4 waves the contribution is cancelled, it's possible that this term now are relevant, you know.
That's my question. So it is possible. Okay.
Yeah, so that's possible. So I mean, this is it's a non-trivial question. I mean, this is.
No. Yeah. Okay. Thank you.
Okay. Some other questions. So, and I was thinking about elastic wave again, coming back to that. So the K equal to the condensate is not K equal to 0. So if, let's say we have the string, you know, or a string of size L. So if there's inverse cascade, then the lowest wave number is that single sine wave. It has to stop there. There can't be anything else.
I don't know. I mean, this is, I think, under development. I don't know what is the answer. This is really.
Okay. There's a raised hand. Who's raised hand? You can, Vishwanath, please unmute and ask.
Hi, Sébastien. It's a great talk. So I just a stupid question. So you have been studying this in decaying setting, right? So start with the initial condition and you're letting evolve and you observe the cascade developing. But what about the force situation? Is it meaningful? And the force situation actually.
Yeah, I didn't study that because it's more complex. As I told you, the system is very sensitive and it requires to use a very small time step. If I force the system, I don't say that it is impossible, but I wanted first to do this analysis, which is less complex than for forced turbulence. But with forcing, in principle, I mean, if it is not too strong, it must be small. That's the problem. It must be small. And as I told you, for the last simulation, it takes 45 days. So if you have an instability after 30 days, you know, you have to come back to the beginning. So this is more, I mean, the system is very sensitive. So this is one point that I would like actually for the future to understand. Is it possible to code this equation differently to avoid this kind of problem and increase the time step? And then it will be much easier for parametric study with forcing, no forcing, and so on. But for the forcing, yes, I want to do that.
Actually, yeah, I should have been slightly more specific. I mean, you're very correct in saying, you know, it will depend a lot on the nature and, you know, the forcing, or even with the decaying, one has to watch out for what is going to happen. But with the forcing, so can we think of the physical situation where it will become important? I mean, actually, that is what I wanted to ask, and how important and relevant that would be with force case.
Yeah. Okay. So let me just say, without forcing. Without forcing, the scenario of production of condensate and so on can be, I mean, exists because of the explosive inverse cascade. I mean, all of that can be present. So that's why, I mean, it is also another reason why it is relevant to do just decaying turbulence. With forcing, of course, I mean, if we want to model the primordial universe and we imagine that we have forcing at, I mean, many sources, then we must include this forcing and see what happens. The result is, I mean, the result that we can expect is that with forcing, the explosive cascade will be even faster. I mean, we have a source, so it will be, you know, and we can even imagine that we have a kind of intermittency at large scale. You know, we force and then we excite, and it's maybe there is a phase of inflation, then it stops, and then again.
So you mean in the inverse cascade region, there could be there could be intermittency.
Exactly. Usually we talk about intermittency at small scales. I mean, because of the cascade. But in this case, in this problem, my feeling is that we can even think to have intermittency at large scale. And usually, I mean, for, you know, if I come back to cosmology, people say, well, we have a phase inflation, and we can imagine different phases of inflation depending where you are in the universe. But well, maybe there is, you know, different. Maybe it happens, I mean, in an intermittent way. I don't know, but that's
okay.
It's an open question.
Yeah, another stupid question is just because I do not know the subject. Is that you? I mean, for example, in this wave turbulence studies, we put this hyperviscosity, right? Often, and you have also used in your DNS. I mean, some some dissipation at the large K.
Yeah.
So just in a realistic setting, I'm not asking like, you know, how justified or not justified that is, but what are the mechanisms that will be very effective, or we should consider, you know, for realistic cases?
Yeah, this is not a stupid question. This is a very difficult question, because for the hypoviscosity, I used hypoviscosity just to really for numerical stability. And we can imagine that in reality, there is no viscosity at large scale. For small scales, it is different. There are papers where they explain with a kind of Landau effect to have a damping of gravitational waves. So I would say there are not a lot of papers. I know at least one paper where it is discussed. And this is, I would say, again, an open question. How can we dissipate at small scales? By what kind of mechanism? This Landau damping means that matter can dissipate gravitational waves. Another way to dissipate, or to have an action lack dissipation, is if we go to small scales with a direct cascade, at some point you will reach the Planck scale. So then your equations are not valid.
Yeah, exactly.
Does it mean that
I was going to ask, you know, in the follow-up, because this is a hydrodynamic description in some sense, and then what happens as you keep going down and down, and how do you touch base with the other theories, like, you know, which are more basic?
Yeah. Well, this is again, I mean, I don't know precisely when we reach the limit of validity of the Einstein equations. Then your description anyway becomes wrong. So yeah, that's another problem. But again, I mean, physically, since my feeling that physically, since the inverse cascade is very fast, all the dynamics will be driven by this physics before the small scale physics. So that's a way to say, well, we don't know at small scales, but anyway, it should be not too much important for the physics.
Okay. And in the same context, I mean, you mentioned something that at the large scales, friction is not important, or there's something that can play the role because
no,
it can limit the formation of the condensate if there's something like that.
Yeah, first of all, physically, I don't know any paper saying that we can have dissipation at large scale. So it was really for my simulation with this diffusion model. Now, if we have hypodissipation, then of course, it will actually limit the condensate. It will act against the condensate. So, but however, there is something else that you must take into account. Let's forget the hypodissipation. You form the condensate, and then physically, that means expansion. So that means dilution. So dilution is a kind of dissipation, in fact. Dilution means that at any scale, you will decrease the amplitude of the metric. So physically, this is, an important, probably the most important effect at any scale that you have if you have inflation, or expansion.
Okay. Thank you very much, Sébastien.
Thank you for your question.
Okay. Okay, I think Vishwanath, you mute. Okay. Any other question, please? It looks like there's none. So I just want to ask one small question. So what are you simulating? Is simulating the full Einstein equation without lambda and without source? Yes,
this is okay. Let me just see if I have the equations here, because I have. Oh, this is just a movie actually. This is initial condition at large scale, so you see the space-time fluctuation. Now, this is a simulation of the Einstein equations with the Haddad-Zakharov metric for an empty universe and without the cosmological constant. Okay.
So what is the time stepping scheme we are using for this?
So again, the numerical scheme?
Time stepping scheme, time step. Or what are you using?
I used here, it's just Adams-Bashford, Cronk-Nicholson scheme, and with the time step of, it depends of your program, but.
Really, so it's energy conserving, no? We have discussed, so some schemes like Euler equation, we use basically leapfrog, or so you may try some schemes which may give you better accuracy. So that may help better, more stable. So there are some schemes which we tried for Euler. That's also unstable.
Yeah.
But so I think it's a suggestion, so you can try some more accurate schemes which may be.
Yeah. So the thing is that when I say unstable, I would say in any problem for MHD, if I increase the time step, then at some point I will have some problem. So, or maybe just, so when I say it non-stable, in a sense that I would expect to if I compare with Navier-Stokes, to do a simulation at 500, at 512 squared with a time step of like 10 to minus 2. Normally it's fine with energy 1. But in my case, it's 10 to minus 5, in fact. But maybe it's because just the equations are different. So, that's...
The CFL, I think there's a CFL condition.
Yeah, there is
there as well.
Yeah.
So I guess if you're satisfying the CFL condition, and if you use accurate enough scheme, I don't know what is causing this instability. I didn't. That maybe you'll look at all that stuff.
Yeah, but I need to investigate more this question. I used actually the schemes that I knew for MHD and so on. That it works very well. So I feel confident with that, so I used it. But
Adam-Bashford may multi-step, so that may be a problem.
Yeah.
So replace Adam-Bashford by RG3, maybe that will help. Okay. Anyway, so I think we can stop now. So great. Sébastien, it was very nice discussion and talk. So
thank you. Yeah, thank you very much for this invitation and your questions.
It's a pleasure. It was great.